Might do some Excel stuff today. We'll see when we have time for it. So, I put up the next Connect homework. So it's going to be kind of over confidence intervals, hypothesis testing for two populations. So as you kind of work through the material, you should be able to start kind of chipping away. The order of it kind of follows the order of which we're going to go through stuff in class. So we can start chipping away at that. I put this up there just kind of introduction. We won't start regression analysis until the Monday after Thanksgiving. I don't know. I might change this. It might be, or sorry, the Monday before Thanksgiving. I might add some other material, but kind of before that Monday, if you want to go through this, it might kind of help you with primer and what we're going to talk about. It's pretty different from what we've been doing. Excel assignment due at the end of the day today, so I'll try to get those graded relatively quick, hopefully before we meet Wednesday. Possibility, maybe not until Friday, but the other thing you'll kind of see pop up there is I'll probably, once this Excel homework is passed after class on Wednesday, I'll probably put up the next Excel assignment. Okay. And then we'll have an individual assignment that's going to come after that. Okay. Questions from me before we kind of jump into material? That's kind of where we're going with things. So we left off and we were doing confidence intervals and hypothesis testing for two populations. So we looked at means and said, if we want to find the difference between two groups' sample means, we can build a confidence interval, and it's really the same exact way as what we were doing before. We're just going to take the sample statistic we're interested in, now the difference in sample means, go a certain number of standard deviations to the left and the right. If that's the number of standard deviations I want to go, I then multiply it by the standard deviation of that statistic I'm interested in, the difference in sample means, which we said was just take each group's sample mean variance, which is the original variance for that group over its sample size, add them together, and then we didn't want the variance, we wanted the standard deviation, so we take the square root. Okay. So with proportions, I think I kind of showed you this at the very end of last class. Right? We know that each sample proportion is going to have this as its variance. Right? So a similar sort of idea, if we want to build a confidence interval, we're now looking at the difference between sample proportions. Just like with one population, if we're using proportions, we can always use that standard normal distribution. And then if that's the number of standard deviations the way I want to go, I'll multiply that by the standard deviation of that difference in sample proportions, which, right, if the variance of the difference in sample proportions is just the variance of each one added together, and then one of the standard deviations, so we take the square root. The only difference is here, it should follow whatever that true population proportion is, but we can't observe that. So we're going to use our best guess, which is the sample proportions that we see. Okay. So it's still following the same sort of format. It's going to look kind of like one population stuff, just with twice as many moving parts, right? But looking up this z-value is exactly the same. Alpha, we kind of treat the same. It corresponds to the same confidence levels. The procedure hasn't really changed at all. Okay. So, whoops, here's kind of our, I've already got this up on the board, but this is what going to be the confidence interval equation that we can use for proportioning samples. Okay. See, I'm making sense, kind of seeing the connection word. What we've done with one population, kind of what we did with two population means last class, and now just kind of extending that to proportions. So, you know, the steps look no different. All right, we identify the piece of information we were given. Now it's just going to be two sample proportions, two sample sizes. Figure out what that z-score is that corresponds to having alpha over 2 on each side of my interval. And then it's just a matter of plugging things in. Okay. So we can kind of look at an example and think about how do we interpret these confidence intervals. And then we'll go to hypothesis testing. So let's say I had this survey, bless you, that had 84% of people in 2011 favored insurance or healthcare coverage for everyone, and 607 people were in that survey. 2010, 82% were in favor, with only 600 people in that survey. What would the 99% confidence interval be? The difference between 2011 and 2010. So whenever we're looking at time periods, we generally always take the newest time period minus the oldest time period, because you can kind of think about here. 11, yeah. If I'm thinking about, I'm really interested in where the true difference in my population proportions is. I can't see them, but that's what I really want to know. Well, if I do the newest minus the oldest, anytime this is greater than 0, right, or these differences are positive, that would mean that rates are increasing, right? Whereas if I flip it around, it kind of goes counter to how we would usually say it, right? I don't think about like today rates are usually I think about today rates are higher. I don't usually think about yesterday the rates were lower than before. And you can say it either way. It's just general. We always kind of put that newest time period first. And when we get to hypothesis testing, I think it'll make a little more sense why this is a little bit easier to talk about. But this is kind of what we're thinking about, right? The difference between these two time periods. We want instead to build a confidence interval. So we've got our sample proportions. Whatever that difference is, we'll build our confidence interval around that. So here, which of these can I rule out? Can I rule out any of them? So if I plug in my sample proportions here, I know that what value should be smack dab in the middle of my confidence interval. Yeah. Yeah, right. Whatever the sample difference I found was, that's where I'm basing my confidence interval around. Because that's the best guess I have of where that true difference is. So you look at kind of 0.84 minus 0.82. 0.02 is that difference I found. So I'm building my confidence interval around that. C doesn't make any sense. 0.02 is not even in that interval. If I'm looking at the other ones, it looks like kind of it's in the middle of all the other three. So there's nothing else I can rule out there, right? But just looking at these, I would know C makes no sense based off of the sample difference that I found. Okay. From there, right, we've got our sample proportions, our sample sizes. I mean, if we write this out, now hold off a second here. So we've got what? 0.84 times 1 minus 0.84 divided by 607. What? 0.82 times 1 minus 0.82 divided by 600. So once again, I would probably break this down and find this first, just so I have one value to plug into that formula. Right, as opposed to doing it all at once, I would kind of create an intermediate step. You don't have to, but I think it sometimes by hand makes it a little bit easier. The only thing left we have to do is find that z-score that corresponds to whatever alpha over 2 that we wanted. So here, if I wanted the 99% confidence interval, alpha should just be 0.01, right? The percent outside that interval in decimal form. So I'm thinking about, I want the z value that has what? 0.01 over 2. Or 0.005 on each side. Okay. So I'll go to my standard normal table. I'll show you two ways of doing this. So here's the first way. So where is the closest value to 0.005? Looks like it's in between these two. So negative 2.57 and negative 2.58. Right? Now we already kind of have that. When we're looking up this z value, we're thinking about the number of standard deviations. Sorry, we want to go to the left and the right to get alpha over 2 in each tail. Well, if I look it up in the table, I'm going to always be looking up that area to the left, so I'll always find negative 2.58. That's already kind of built into my confidence interval equation. So really all I need to do is plug in the absolute value. Right? Or subtract that many standard deviations to get my lower bound, add that many standard deviations to get my upper bound. Any questions on kind of how I found that or anything kind of here? I mean, this should, like I said, starting to look kind of like we're doing the same procedures, so things should look similar. What I could have also done is know that I want 0.005 in that tail. Go down to this very last row of my student T. We said this kind of gives me the comparison values that I would find from a standard normal. I can be a little more precise even because it gives me it out to the third decimal. Okay. So kind of two ways to do that, really, whichever one you're kind of more comfortable with, right? If it's easier to just use the z table because you know that's the value you're looking for, that's fine. But remember, those z values are actually kind of nested in that student T table in the last row. Okay. Any questions there? Okay. So what can we say based off these two samples that we took? So this is where we want to start interpreting these confidence intervals. So I've got negative 0.036 to what? 0.076. So here, what can I say about the views over, I think this one was a survey done, I think I said Indiana. So the views in Indiana were what happened to them over time, right? So remember, this was how favorable people viewed healthcare coverage for everyone, or kind of like mandatory healthcare coverage. So here, can I say, did views become, or did it become more popular, did it become less popular? Did you know, favorability of this go up or down? I can't actually say anything here. Why? Yeah.
Is it because 0 is still in the middle of those two?
Yeah, the easiest way to probably think about this is if 0 is in my range of possible values, then one of the possible values for this difference is 0, which means they're exactly the same, right? So it could be that views haven't changed at all because 0 is one of those values in my confidence interval. Now, another way of thinking about this is the reason I can't say whether or not views have went up or down is not only because 0 is in that range, but it could be that views have went down, right? I've got a negative difference. Could be that they went up, right? And the reason why, if you think about it, we found a sample difference of 0.02. If the true difference was something like, I don't know, negative 0.01, well, it's not that unlikely maybe that we saw 0.02 from our samples, right? Or for the sample difference there. So here we can't really make any statements, at least at the 99% level. But let's kind of review what we've been talking about with confidence intervals. What if I maybe wanted to say this at the 90% confidence level? Why might things change? If I want to say this with 90% confidence, I still have my same two samples. What's changing up here? So going from 99 to 90%, alpha becomes 0.1, so it's going to be larger. So you can kind of think about now I want a larger area in my tails. So what's going to happen to the z value that corresponds to that? It's going to have to become smaller, right, in magnitude. If this becomes smaller, what's going to happen to the width of my confidence interval? Adding and subtracting a smaller value, so it's going to become a little bit more narrow. I doubt at the 90% level it becomes narrow enough, but you can imagine maybe, right, it goes to something like 0.01 to 0.03. Now I've only got positive values in my confidence interval. Maybe with a 90% level, I can say that it has become more favorable, or that views have increased on how healthcare coverage for everyone. Now, like I said, if you work out the math, I don't think it probably gets that narrow that fast, but you can imagine in other examples where maybe my lower bound was closer to 0, it might be enough to where I can say that there's a change at a 90% level, but I can't say at the 99. Okay. Does that make sense when I'm getting that there? I'm thinking about how these are changing with the different levels of confidence. Probably won't spend a lot of time. I mean, really, this is just going to be a matter of kind of looking up these z values and then plugging in the information that we're given. I just use this example because I think it's interesting. I wanted to point something out here, not so much with the confidence intervals, but just data in general. So that same survey looked at whether or not there was favorable or unfavorable views of the Affordable Health Care Act, right? So the Affordable Health Care Act was viewed very unfavorably, about 51% in 2011, 48% in 2010. So did this become more unfavorable, right? Did this unfavorability rating go up, right? We have sample evidence that it did, right? Because in 2011, it's what? 0.51. 2010, it was 0.48. So we found a sample difference of 0.03. But similar to before, like that's not too far away from a value of 0. So let's build our confidence interval. We wanted to do this at the 90% level, right? Or sorry, 99%. Our z value is going to be exactly the same, right? Anytime we're looking at a standard normal distribution, that 99% level will always correspond to an alpha of 0.01. 0.01 divided by 2 is always 0.005. If we look at 0.005 on the table, we'll always find 2.576 or 2.58 if we're rounded to that second decimal. So now it's just a matter of just plugging in. We've got the same sample sizes. It's just that we're looking at different sample proportions now. So it should look pretty similar. Right? And here, I need to probably edit this, but this negative sign for some reason didn't follow with the number. So you can kind of see here, we start with a negative value, go to a positive value. We kind of have a similar thing here. We can't really say whether or not this has become more or less unfavorable, right? Because we have negative values in the confidence interval, positive values, but also that value of 0. Could be that the views are exactly the same, right? So what I wanted to point out here about the data, which is interesting, is, I mean, it's a little bit more of a policy thing. But just notice the levels of these sample proportions. So when we're talking about whether or not people like the Affordable Health Care Act, we've got what, 50% of people in favor? While the main goal of this act was mandatory health care coverage for everyone, which like 80% plus people were in favor of, right? So I just think it's kind of an interesting thing in terms of the framing, right? What do people actually believe? And then maybe politically, just because, you know, they're on one side, they think that they aren't supposed to be in favor of this concept, right? Because they know they're supposed to, or at least Fox News told them they're supposed to hate the Affordable Health Care Act, right? So I don't know, it's kind of interesting thing that kind of comes out in the data. I think I had one more. Oh no, I think I did hypothesis testing. So before I kind of move on from here, any questions on this before we go to hypothesis testing? So we're not reinventing the wheel here. Really, it's kind of very similar things that we've done before. Kind of take like the one population proportion and then the difference in sample mean stuff we did, and we're just kind of combining. So we can do the exact same thing, but we said confidence intervals and hypothesis tests are related. I kind of alluded to this at the end of last class, where my confidence interval is going to tell me this is the range of possible values. Okay? So if I did a hypothesis test for all the values in that range, I should not be able to reject them, right? I should fail to reject the null if I'm assuming that the true difference is somewhere in that range. So if we instead want to do hypothesis testing, before, just to have a comparison, we said, let's look at that statistic we're interested in, the difference in our sample means. We'll subtract the assumed true difference and then divide by the standard deviation of that statistic we're interested in, or the difference in sample means, which we said was just, well, the variance is going to be each sample means original population variance over its sample size added together. And then we wanted the standard deviation, not the variance, so we take the square root. So you probably already imagine what is this test statistic equation going to look like for these sample proportions. Well, I'm now interested in the difference in my sample proportions. We're going to still have these assumed true differences. What did I say I'm going to keep these most often as? Or even in practice, usually this would be what? We made this equation easier. I said usually we're going to have this assumed true difference of 0. Right? The reason why that makes it easier, subtracting 0 doesn't change anything. We're then going to divide by, same kind of format, the standard deviation of the statistic we're interested in, which is now the difference in proportions, which we just looked at for our confidence intervals. Had something that looked like this. Oops. Okay. So this is where things become a little bit different. This is what you would think it would be. We have an added wrinkle that gets thrown in when we actually want to do this test statistic for a proportion, right? So it should be that it follows both of these, but generally, the way we're going to write this is thinking about it as first calculating P bar, right? Which kind of gives us this average kind of sample proportion between the two. And then once we have P bar, we can plug that in here and it looks a little bit different. Now, even though it doesn't follow kind of conventional what we've been doing, it is trying to do the same thing. We'd have to go through the mathematical proof of why we need to do it a little bit differently for the sample proportions. But I can kind of give you an idea why. So one of the reasons why we're going to have to do this is if we're thinking about, we have the statistic we're thinking about is the assumed true difference. Okay? So when I say the assumed true difference is say 0, right? That doesn't tell me about where those two proportions are. Because I could have those two sample proportions be 0.01 and 0.01, right? And the difference would be 0. Or they could be 0.98 and 0.98, and the difference would still be 0, right? But depending on the size of those sample proportions, I know those will kind of alter what the variance is for each of those population samples. I was taking samples from two populations. And so we'll have to calculate the test statistic a little bit differently. But we still need the same things. It's still a function of those two sample proportions as well as those sample sizes. Okay. So like I said, it looks a little bit different, but what's in that denominator is still representing the standard deviation of the difference in our sample proportions. Okay. Any questions here about kind of notation or anything that we've got going on? But once we get to this point, it's just a matter of plugging things in. The same steps of the hypothesis test are the same. We got right, left, two-tailed test, finding p-values, critical values, looks no different than what we were doing before. Right? So we can think about an example, right? We've got, oops, I just repeated them. The exact same steps as when we were looking at hypothesis testing examples. I think this one has it set up for the critical value approach. I'll also kind of show we can also do the p-value approach, and they should lead to the same decisions. So let's work through an example, all right? I think before the last selection, I kind of went out and looked at some of the polling data, and it had, 1,500 people, and 49% of people plan to vote for Biden, 47% plan to vote for Trump. You want to test the proportion that Biden will receive more votes than Trump in the upcoming election. So what would your null alternative hypothesis be? So once again, our alternative hypothesis is always what we want to test for. So we're thinking about the difference, and I think here it says what? You want to test whether Biden will receive more votes than Trump. So you're thinking about something like this. Okay? Now, you don't have to write it out this way. Just for some people, it kind of helps. Like, this is what we want to test for, but how do I write this out in terms of a difference? Well, I can kind of think about it here. If I subtract the proportion of Trump from both sides, I'm then left with that I want to test for, is that difference greater than 0? Right? And maybe that just is intuitive to me. Like if I say I want to know whether or not Biden has more votes than Trump, then when I'm thinking about taking the proportion of votes for Biden minus Trump, well, I know that would have to be positive. If I can think through it that way, that's fine. If it helps to write it out, in terms of how it's said, and then rearrange it so that you have a difference on one side, right? That for some people is a little bit easier. Okay. Is it clear what I'm saying here? Not really. No, yeah. So we want to test for whether or not Biden is getting more votes than Trump, or is that difference between the proportions positive or greater than 0? So that's our alternative hypothesis. We assume the exact opposite is true. Okay. So we've got what? On the test here. I look at my alternative hypothesis, greater than or right tail test, right? So if I'm thinking about my critical values, can I rule any out here? My right tail test, I want to find the critical value that gives me alpha in the tail. So I know that for a right tail test, my critical value should be positive, right? They're on the right side of that distribution. My standard normal distribution is centered around 0. So if I'm looking at that right side, I know I should be dealing with positive values. Now from there, I'm going to have to just look it up. So I've got an alpha of 0.01, or I'm looking at the 1% significant or the 99% confidence level here. We might even start to kind of recognize these. So for a one-tailed test, I could look up just alpha, right? So this is where, you can do it several ways. If I try to find 0.01, I'm in between these two values, I get negative 2.32 and negative 2.33, right? So I use the higher of the two. But I have to remember, I looked up alpha, the table has the area to the left. So I was looking up 0.01 to be in my lower left tail. I actually want 0.01 to be in that upper right tail. So I know, because this is a symmetric distribution, that if the area to the left of negative 2.33 is 0.01, then the area to the right of positive 2.33 will be 0.01. Right? So I will find the negative value, but because I had a right tail test, I know it's going to be that same z value, but positive. Okay. What I could have also done is had this visual and said, okay, what's the actual area I want to the left? Well, if I want 0.01 to the right of this value, the area to the left of it would be 0.99. If I then go look that up in my table, where are we? In between these two. So 2.32 and 2.33, sure enough, I find the same value. Okay. As if I would have just looked up alpha and remembered it was a right tail test. Any questions on this? What would the critical value be if this was a left tail test? See if we're following what I'm saying. Yeah, just negative 2.33. What if it was a two tail test? You may not know the exact number. Why? Because what would you have to do differently if this was a two tail test?
Alpha over 2.
Divide alpha by 2, you would actually want to find the value that gives you 0.005 in the tail. Yep. And then it just kind of goes back to like confidence intervals, right? You've got two critical values. You're going a certain number of standard deviations to the left and the right. So we've got our critical value, right tail test. We can think about here's our rejection region. So the only other thing we really need is our test statistic. We've got that equation up there on the board. Oops. I can get this going here. All right. So I've identified, kind of got the same sample size for each of these. I've got the sample portion for both candidates. And remember group 1 here, we're treating as kind of the proportion of votes for Biden, 2 is for Trump. We've got kind of that Z value, or that critical value we're going to compare to. Now it's just a matter of plugging things in. So I'm going to find this P bar first, right? Or it's kind of like a weighted mean between the two proportions. Now, when I have the same sample sizes, you actually could go back to how you think you should treat this test statistic, right? Where I said, you know, if we did this kind of similar to what we're doing with confidence intervals, but if we didn't have the same sample sizes, we would actually need to kind of use this weighting formula. So I'm just always going to use it so we never make a mistake. And more often than not, we're not going to have the exact same sample sizes. So this is the approach that we're going to want to use. So that denominator looks a little bit different. We first compute P bar, right? Plugging in sample size of 1500, 0.49, 0.47. And then have P bar to plug in. I can plug in 1500 for my sample sizes. I plug in my sample proportions. My assumed true difference should be what here? More often than not, it's always going to be 0. All right, that value that's in my alternative null hypothesis. So this becomes 1.097. Right. So the sample evidence I found was about 1 standard deviation away from that assumed true difference of 0. So if I'm plotting my test statistic here, so here's my Z statistic of 1.097. It's not in my rejection region. So at the 99% level here, I would fail to reject. Okay. Yeah.
Where did you get the 0.48? It's in the denominator.
That was calculating that intermediate value that we now need in our denominator, which is P bar.
Are we going to have to do a calculation like that?
Yeah, so if you're wanting a test statistic for the difference in sample proportions, it looks a little bit different than what we're doing for sample means. You first now have to get kind of this weighted average of these two sample proportions. Like I said, here it's a little bit easier because we have the same sample size, but if we didn't, this would look a little different. It would just be, you know, the middle value in between the two sample proportions. Then once you have that P bar value, plug that into your denominator. So I didn't put that in here, right? 1500 would be your sample sizes. 0.49, 0.47 would be your sample proportions there.
And then it would be 3,000 now there.
Yeah, yep. Yeah,
Okay.
1500 plus 1500.
Yep.
Like I said, when it's even sample sizes, it really doesn't matter, right? Because you just know it's the middle value. But when we have unequal sample sizes, this is where this becomes a little bit trickier, right? But we just always use it to kind of, so we get used to that kind of, because usually we're not going to have the exact same sample size. Any other questions on this? So I want to try to start getting at some of these concepts here. Thinking a little bit more difficult about these hypothesis tests. So we said that we failed to reject here because our test statistic wasn't in that rejection region. Or I said another way to think about that, if the absolute value of your critical value is less than the absolute value of your test statistic, well, there you reject. Ours wasn't, right? Our test statistic was actually less than, right? It wasn't greater than. So we failed to reject. What happens? Let's say I go back out and I find the exact, so this is, you know, I'm trying to predict the election. I find the exact same difference And I think the exact same sample proportions of people who vote for Biden and Trump in the upcoming election. So based off of this, I couldn't predict the election, right? I couldn't, or I at least couldn't say that Biden was going to get more votes than Trump, right? I couldn't reject that value of 0. Couldn't reject that they're exactly the same. I failed to reject it. So it could be that they get the exact same amount of votes. But I did find sample evidence, right, that Biden was going to get a little bit more, 0.49 minus 0.47. I did find this positive sample difference. So let's say I go out again, I find the exact same sample proportions from different samples, but those samples have sample sizes of 3,000 each. Right? Why is it more likely I can now reject the null? So if my sample sizes go up, what's happening to my critical value? Might be kind of a trick question. Nothing. It doesn't depend on my sample size at all, right? All it depends on is alpha. But, right, so I'm still saying if I find sample evidence that's more than 2.33 standard deviations away, I'm okay rejecting, right? Well, I was only 1 standard deviation away when the sample size was 1,500, but if instead the sample size was 3,000, what's going to happen in my equation? I don't have to worry about p-bar too much here because these going up isn't going to change the relative ratio. But when these go from 1,500 to 3,000, my sample size is getting larger. What's happening to these fractions? They get smaller. Or when I have higher sample sizes, just like with one population examples, that's always driving down the variation I see in my sample statistics, right? When we just had so this was kind of a variance. If we just had one proportion or one population, the variance of my sample proportion, right? You can kind of imagine maybe a little bit easier. My sample sizes are getting larger. That variance is getting smaller, right? The variance is getting smaller, so is the standard deviation. So I jack up these sample sizes to 3,000. My standard deviation is going to get a lot smaller. Now seeing the same sample difference, it's still 0.02, but maybe before the standard deviation was about 0.02, so it's only 1 standard deviation away. Well, if this was sample difference was 0.02, but now after the higher sample size, my new standard deviation I know is going to be smaller. Maybe it's like 0.01. Well, maybe now I get a test statistic that's 2, which even if I can't reject the null, at least I know it's a little bit more likely, right? My test statistic when I'm getting higher and higher sample sizes would be moving in the direction of which it's going to become more likely I could reject the null. Okay. Assuming I found the exact same kind of sample proportions there. That's kind of the general idea, which is why we like high sample sizes, right? Because even finding the same sample difference, I might be able to reject that value of 0 because I've got such a large sample. Any questions on that, or if I want to kind of stay in there? And I'm trying to talk through all of it. Like, if you can just remember higher sample sizes, like make your test statistic way larger, so then it's more likely it's in the rejection region, that's fine. But how it's operating is that these higher sample sizes here are driving down that standard deviation. Well, then finding the same sample difference is going to be more standard deviations away from an assumed true difference of 0. Questions on this before we keep moving here? All right, I think I've got another example because I kind of wanted to match this up to what we did with confidence intervals. They kind of help show something that I had mentioned last class. So let's say I've got the exact same example as I did before, where I'm thinking about people being in favor of healthcare coverage for everyone. So let's say I want to test the proposition that views are different in 2011 than they were in 2010. Okay. So what would my alternative hypothesis be there? Well, first of all, which of these should I be able to rule out very quickly based off of what I see here? Yeah, if I see this term different or different than, I should be thinking about a not equal to sign in my alternative hypothesis. Because really what I'm saying is the sample proportion in 2011, if it's different from the sample or the true population proportion in 2010, I'm saying, are they not equal? Are they different from each other? Are they not equal to each other? Well, I need my hypothesis test to be in terms of a difference. So I rearrange things a little bit, subtract that proportion of 2010 from both sides, And I've got, oh yeah, I'm thinking about, is that difference something other than 0, right? Because if the views are different in both years, then when I take the difference, it's going to be some other value than 0, right? The only way it would be 0 is if they were exactly the same. They weren't different, right? So I'm trying to test for whether or not that difference is anything other than 0 or not equal to 0. I'll assume the opposite is true, which is that it's equal to 0, okay? Any questions on kind of identifying that or why we write the null alternative that way? Yeah.
Well, I just have a quick question. So,
Mhm.
when we're determining if it's a right or left tail test, I forget, do we base that on the alternative or whatever it is?
Yep.
Yeah.
So do we have, what type of test do we have here? Well, not equal to sign. Yeah, two-tailed test. Yep. So once again, I'm usually giving you 0 values, so hopefully B and D also look a little odd. I said I'm only going to give you on the exam and also in the Excel homeworks kind of this assumed true difference of 0, right? So that makes it a little bit easier. We're going to have kind of this null alternative hypothesis. Okay. From there, it's really very similar to what we just did. We've got our test statistic equation. The assumed true difference is 0. Our sample proportions now are 0.84 and 0.82. We've got different sample sizes now. So when it comes to, let's skip ahead a little bit, calculating that test statistic, we're going to first have to find that p-bar value. So how am I getting that 0.83? And actually, if I calculate, I'm rounding it to the second decimal. If you go out further, it's going to be a little bit different than 0.83. But I would plug in my sample proportions of 0.84, 0.82. Sample size is 600, 607. Usually, like on the homework, if it asks you for a test statistic like this, it'll tell you round the intermediate calculations. It's talking about like p-bar to the 4th decimal or whatever decimal it kind of suggests. Okay. So here, right, we've found p-bar. Now it's just a matter of getting all of those values plugged in. We plug in p-bar, 1 minus p-bar, sample size. We can test this of about 0.92. So, this is, I'm not wasting a lot of time because really you're going to have the formulas in front of you. Calculating the test statistics, probably not the question I'll ask the most of on the exam because I'm more interested in that's just computation. Once you have that, how do you determine whether or not you can reject, right? You compare that to your critical value. So what would the critical value be for the 99% level, right? Or the 1% significance level? Oops, sorry. I didn't go back far enough, did I? There we go, all right? Well, you already saw the answer, right? But how could I find it? There's actually a couple ways, right? So I'm looking at proportions. I've got a two-tailed test. So, right, I want the pair of critical values that gives me alpha over 2 in each tail or 0.005 in each tail. Now we actually looked this up earlier. So when we looked it up earlier, we said it was going to be 2.58. So how did I get this out to the 3rd decimal? Just to kind of review, I could have used that student T table. That area I wanted was 0.005 and then went to the very last row. It would give me the standard normal values, but out to the 3rd decimal. So I've got my critical values of negative and positive 2.58. Okay. Any questions? Now, my test statistic was like less than 1, so I'm going to fail to reject or reject the null. Will my test statistic be anywhere close to those rejection regions? It's going to be like right here, right? So no, I would fail to reject the null, right? I didn't find sample evidence that was more than 2.58 standard deviations away from that assumed true difference of 0. So it's very possible that that assumed true difference of 0 could in fact be the true difference. Now, what if I wanted to find the p-value here? Right? And maybe a little bit trickier. The p-value is the probability I saw the sample evidence I did, or anything even further from that assumed true difference of 0. Okay? So here, I found this positive test statistic for a two-tailed test. I want to find the area to the right. But does that represent my p-value? Close, but what type of tail test do I have? Two-tailed. So once I find this area to the right, that's not my p-value, that's just half of my p-value. We said there's one more step, right? I need to multiply that by 2, right? So if this is half my p-value, when I multiply it by 2, I get my total p-value. And that was because it would have been equally as likely now that I saw sample evidence on the other side, but that also goes against my null now. Before, evidence on the other side supported the null, so we didn't have to multiply by 2, right? It was just kind of just the one tail, right? So I'm going to look up my test statistic, and now I have to remember what the second decimal was. Was it 9.25? So we'll round this up to 0.93. So I go to my Z table, I look up 0.93, and I get 0.8238. Okay, so 0.8328, multiply it by 2, I get 1.6 something. Why do I know that can't be right? A p-value is the probability, so it has to be less than 1. So what did I do wrong here? When I looked up that test statistic of 0.93 on the table, nope, so we're dealing with proportions. So proportions are always the standard normal. But what does the standard normal table always tell me when I look up that Z value? 0.83 is not the area to the right. It's actually the area to the left of that Z value. So to find the area I wanted, that area in the right tail, I should have been subtracting that from 1 and then multiplying it by 2. Okay. So it's a little bit tricky if I've got a two-tailed test and I find a positive sample difference or end up on the right, because I'm gonna have to remember when I look up that Z statistic or that Z value, the table's always gonna give me the area to the left, but I need the area in that right tail. Right? And then once I have the area in the right tail, it's a two-tailed test, I'll multiply that by 2. Now, if I do that, I'm gonna get what, like 0.34-ish, right? So 0.17 times 2 is about 0.34. So this would be my p-value. What levels can I reject that? Well, I only reject if that p-value is less than alpha. So if I've got a p-value of 0.32, or sorry, 0.34 approximately, is that less than 0.1, 0.05, or 0.01? It's not going to be less than any of those. So I'm going to fail to reject at every level, which if I go and find the critical values for the 90 and 95%, or the 10 and 5% significance level, I'll come up with that same rejection decision using the critical value approach as well.
So in the two-tailed, once we find that one p-value, we have to multiply that by 2.
Yeah, so be careful. It's not once you find the p-value, it's once you find the probability of seeing the test statistic you did or anything more extreme. It's just the definition of the p-value isn't the test statistic that you found or anything more extreme. It's the probability you found something that goes against the assumed true difference. Well, your test statistic is evidence that it goes against that assumed true difference. But for a two-tailed test, it would have been equally as likely you had something on the other side. So that's why we have to multiply it by 2 to get the entire p-value for a two-tailed test. Does that answer kind of what you're getting at? There's something I wanted to mention earlier. Let me think. Oh. Okay, I'm going to draw these out again because this is becoming a mess, but I'm going to be using these critical values. Remember, both of these tests, we had a right and a two-tailed test. We're actually both at an alpha of 0.01. So I want to kind of highlight something here between these two examples and kind of point out the differences. And I think I've mentioned this before, but the difference between the difference between a one and a two-tailed test. So here we had our two-tailed test. And here we had our one right-tailed test here. My critical value was 2.33. That gave me an alpha of 0.01. And then here, my critical value is negative 2.58 and positive 2.58. And that gave me 0.01 total in the tail, or half of alpha in each tail. Right? So why is it more difficult to reject the null when I've got a two-tailed test? So if I have a two-tailed test, what's happening here? Well, then when I go to look up the area in the tail, it's always going to be half as large. So if it's always going to be alpha over 2, I know my critical value is going to be a little bit larger in magnitude. Well, remember, we said that we only reject if my test statistic or the absolute value of my test statistic is greater than the absolute value of my critical value. So even if I had the same sample evidence, but instead of running a right-tailed test, I ran a two-tailed test on that same assumed true difference of 0. Well, notice my critical value becomes larger. My critical value becomes larger. Having the same sample evidence, it's actually going to be less likely that I can reject the null, right? And the reason why is because going into a one-tailed test, it's almost like we're shutting down that the difference could even be on the other side. I think the example I gave maybe was like male female height. Like we know the difference is going to be positive, but we might just want to know like how positive is it, or how positive is that difference, right? Or what's another one that we kind of would imagine that we're only going to find positive values, but is it enough to ignore 0? Probably something like income, comparing it to like two age groups, 20s to 40s. Like you're almost like, you know, the difference because people are at their mid-career salaries, that difference is going to be positive. So you probably would just want to do a right-tailed test, right? But if you don't know what that difference is, maybe I'm just looking at the difference in salary between, engineers and finance majors, right? I don't know if it's I don't know which way that difference goes. I might be doing a two-tailed test, but inherently doing a two-tailed test makes it a little bit less likely I can reject the null. It's just harder, right? And you can kind of imagine, like, let's say I found a test statistic of 2.4. Well, if I was running a right-tailed test where I had that I assumed the difference was less than or equal to 0, right? Well, I can actually reject that it's less than or equal to 0. Right? It sounds kind of weird, but if I was doing a two-tailed test instead, where I just assume that that difference is exactly equal to 0, well, seeing that same test statistic of 2.4, now I would actually fail to reject that true difference is 0. Right? So it's kind of counterintuitive because they're both really looking at that same value of 0. It's just that the reason why it becomes harder to reject for a two-tailed test is because you know that, yeah, you saw the sample difference that you did, but it would have been equally as likely there was something existing on the other side that goes against the null. In a one-tailed test, the other side never goes against the null, so you don't have to kind of multiply that probability by 2. Okay. So I just wanted to kind of point out, like, even if we found the same test statistic there, it's a little bit harder to reject for a two-tailed test. Okay. Any questions over kind of anything just conceptual that we've talked about today? Or so let me think what I want to do. So I think what we're going to do on Wednesday is I'll probably go through pretty quickly because it's not a whole lot different. The difference in sample means when we only have sample variances. The format of the confidence interval and hypothesis test look exactly like what we were doing for the difference in sample means when we knew the population variances. It's just now we plug in the sample variances instead of the population. So the format looks the same when it comes to the test statistic and confidence interval. What do you think the only difference is going to be? We only have sample variances. Can't use the standard normal. We have to use the student t. Just like when we had the one population examples and we only had the sample variance, we had to use the sample t. So we'll work through a couple of examples by hand, but then I'll kind of transition into showing you how we do this. Now, I've already showed you how to do it with one population. It's going to be exactly the same. It's just that the test statistic equations are going to be a little bit different for two populations. So I'll show you how we do some of this in Excel. I've actually already got the kind of blank file up there in the in-class data folder. So we'll kind of start working on that. And then we'll do matched pairs stuff on Friday. Okay. All right. So one thing I'm also going to do, so you like what you're saying, I'm going to put up like a short 3-question quiz, kind of just having you work on some of these hypothesis test competence interval questions, just to kind of see where everybody's at. If you have some time to work through them, also just good for you to start kind of trying to actually work through some of these. Okay, so I'll get that posted this afternoon. I'll be due before we meet in class on Wednesday.